Okay, welcome to Introduction to Quantum Mechanics course, and this is my name. This course is given in English and is about to bridge between, say, modern physics and the graduate level of quantum mechanics. So let me just follow this note. And my name, my email. So this is the textbooks that we will be using for this course, and you already learned that previously. So it's called Quantum Physics and written by Gazarovich. But there's also another useful reference book, which is oftentimes a textbook for other introduction to quantum mechanics. The title is exactly Introduction to Quantum Mechanics by Griffiths. Basically, I will follow Gazarovich's textbook, this one, but not all of them. So I will skip many introduction level of the quantum physics, the early chapters of this book, because I assume that many of you have already taken this modern physics course. Well, then there is a compromise, because we already have this course in our department, and which is the prerequisite course for this Introduction to Quantum Mechanics. And this Introduction to Quantum Mechanics is the more advanced course compared to the modern physics. The modern physics is the more elementary level of the quantum mechanics. All right? Okay, so if you have not learned this, and learn it now at the same time, because I will not wait too much for those of students who have not taken modern physics beforehand in advance. So I'm sorry for that, because we need to move on. So this course is not about the modern physics. It's not about introducing quantum phenomena from the scratch, from the very beginning. For example, from this photoelectric effect for Compton scattering and so on and so forth. No, this is not a course about origin of quantum physics. It is about what? Quantum mechanics. But of course, in order to introduce the quantum mechanics, you need to go back to the quantum physics. So we'll probably go back and forth between the modern physics, quantum physics, and quantum mechanics. So in the very beginning of this course, I will probably use at most 2 weeks, probably 1.5 weeks, to give you a very broad review of the modern physics that some of you have not learned. This is the only chance that you pick up this concept of modern physics, namely the history of a quantum theory or quantum mechanics, starting the late 19th centuries until early 20th centuries. And this part of the history of quantum physics, I will call this belonging to this modern physics category. So I will not repeat what you already learned in modern physics too much. Of course, there will be some overlap or some review necessary, but this modern physics level is not our primary goal of this course. So I guess this is pretty clear. When we go from quantum physics to quantum mechanics, we need some sort of a review of your modern physics and quantum physics knowledge. Okay? Nevertheless, the modern physics is not our primary goal. Our primary goal is to introduce more advanced quantum mechanics, a way to calculate the quantities that you could observe in the quantum world. So that's the purpose. So this technique or this more mathematical tool allows you to really calculate something. And we do not stop at the phenomenological level to just see what kind of a strange phenomena that come from the quantum world. No, we should learn how to calculate these quantum mechanical systems. Okay? The way we calculate the quantum mechanical system is to learn quantum mechanics. But of course, this is not a graduate level quantum mechanics, and the purpose of this course is to take the bridge. So this is the modern physics, and this is the graduate level quantum mechanics. And our course, Introduction to Quantum Mechanics, is actually a bridge between these two. Okay, and that's the role of this course, playing this core course of our department, which is to introduce quantum mechanics for the undergraduate students. And once we know this elementary level of quantum mechanics, then it's easy for you to actually learn the more advanced graduate level quantum mechanics. Whether you are attending graduate schools in physics or not, it's your option, but this course is the bridge over this more phenomenological approach to the modern physics and the more mathematical graduate level quantum mechanics. So it's a mixture of the two, but we'll put more emphasis on how to really learn this graduate level quantum mechanics, given the fact that you only learned modern physics. And this is a very interesting course because you not only have a chance to review your modern physics knowledge, but you also have a chance to really see how this works. So what is the fundamental principle behind this quantum phenomena, which is the principle of the quantum mechanics. So you're about to learn this in a more rigorous and mathematical manner. So by the end of this matter, I hope you will appreciate the concepts and mathematical techniques that will be introduced in this course. So let's just talk about the outline. So I will very quickly go through beginning chapters of this book. For example, chapter 1, 2, 3. So I will probably go very fast, especially chapter 1. I leave this to you as a reading, not homework, but a reading task at home, that you review the chapter 1 of this book and see how much you get or remember from your modern physics course. And the chapter 1 is a history of the birth of the quantum mechanics, starting from the late 19th century and continue till, say, early 20th centuries. First of all, so I'll give you a general review of modern physics, or the key concepts in quantum mechanics that you already learned, but you may not remember by now. Okay, so let me remind you the most important concepts in quantum mechanics in the very beginning of the course, which allows you to really refresh your memory. And this will take probably 1.5 weeks. So, and this is the excellent opportunity for those of you who have not taken modern physics course. This is the only chance that you could review your introductory level of quantum physics. Then we will move on. So after this brief review, we will start to introduce quantum mechanics, which is the general mathematical structure of wave mechanics. And we will apply some knowledge in linear algebra to reformulate the, say, Schrödinger equations or this probability amplitudes in quantum mechanics in a more mathematical way. Okay? So linear algebra or vector analysis are the tools that define the mathematical structure of wave mechanics. Then we will introduce the operator method. So as most of you have learned that in quantum mechanics, when we take the measurement and we already disturb the system, so we interfere the system by taking the measurement. And there are some key concepts such as the eigenstates of a quantum system and this particle wave duality and Heisenberg uncertainty relations and the probability interpretation of your measurement and so on and so forth. And so these are the key concepts in quantum mechanics which we will introduce in the following 2 weeks or so. And then we introduce the mathematical structure of the wave mechanics and operator method in quantum mechanics, meaning that whenever we would like to know some quantities in experiments, we should take the expectation value of that corresponding operator. We take the ensemble average of a quantum mechanical operator, A, in order to know what is the expression value of such measurable quantity, which is defined as A operator. For example, spin, or orbital angular momentum, or Hamiltonian, which stands for the total energy of the system, and so on. Okay, so whenever we want to know experimentally measurable quantity, so we should define in quantum mechanics the corresponding operator for that measurement. And we need to take the measurement of such an operator in order to see what is going on there for our interest of quantity. So we will introduce this operator method in quantum mechanics. And then we will go to the angular momentum and then Schrödinger equations in three-dimensional hydrogen atom. This is a well-known problem which I believe many of you already learned this in modern physics, but not in great detail. So we will solve this three-dimensional hydrogen atom by solving the Schrödinger equation for this, and then we analyze the solutions of this hydrogen atom. And then we should move on to study the matrix representation of operators. So many quantum mechanical observables that we can define operators corresponding to that measurable quantities could be represented as or by a matrix. So it's always possible to actually represent quantum mechanical operator in a matrix form. For example, n by n. For example, spin angular momentum. So it could be represented by a Pauli matrix made of 2 by 2 matrix, and angular momentum operator, and also Hamiltonian, for example. So almost all quantum mechanical operators could be represented by a matrix. And we could take the eigenvalues of such a matrix operator. The eigenvalues represents this characteristic energies or spin, angular momentum, or whatever quantities in your system. So, and they are quantized. Okay, meaning the eigenvalues labeled all possible quantum states that allowed this quantum particle to occupy it. Okay, so you have, say, for example, this spin 1/2 electron can take either spin 1/2 h bar or minus 1/2 h bar as their angular momentum eigenvalues, and as a result, by diagonalizing this 2 by 2 matrix, you could find out what this possible eigenstates or angular momentum values that a single electron can take. Okay, and so on and so forth. So we will learn how to formulate this operator in quantum mechanics in matrix form. And then we introduce spin. So we may take up to 2 weeks to introduce angular momentum operator, and so for the spin angular momentum operator. Okay, so let's take a very brief break, and then we will, I will continue introducing the remaining topics of this course. So the remaining topics include time independent perturbation theory, and if we have time, we can introduce collision theory. And I think that should be enough to claim that you learned Introduction to Solid State Quantum Mechanics. So let me just finish this outline. We may not have time to talk about the last two topics, namely the interaction of charged particles with EM fields, and also collision theory, but these are very important in this graduate level quantum mechanics course. And of course, there's a time-dependent perturbation theory. Again, I put a question mark, meaning that we may not have enough time to discuss time-dependent perturbation theory, but my goal is to at least introduce to you this time-independent perturbation theory, which is very crucial when you study graduate level quantum mechanics, or when you really try to calculate, this interacting systems, and you cannot find exact solutions from solving Schrödinger equations, and therefore the only option is that you do perturbation theory, and this is a systematic way to estimate your eigenvalues and eigenstates order by order fashion as a power series of your interaction strengths. So let's just start introduce this, the key concepts in quantum mechanics. By the way, this one-dimensional potential problem that many of you have learned in modern physics will be reviewed here. But I hope that I can very quickly review this quantum tunneling problems and potential well, potential barrier, and simple harmonic oscillator problem, and so on and so forth. Okay, so I suppose many of you know what I'm telling you in these plots. Okay, so this is just a review of a modern physics lectures that you study the Schrödinger equation for a one-dimensional potential problem. So let's talk about the key concepts in quantum mechanics. So there are a couple of key concepts in quantum mechanics that are related to one another, and I use a diagram to summarize these key concepts. So the first one is the particle-wave duality, which says that the particle is wave, and say electromagnetic wave is a quantum particle. And this is best illustrated in these two experiments or theoretical proposals. One is the de Broglie hypothesis, and later confirmed that indeed all quantum particles, even if they look like a particle, they show off a wave features, wave-like features, and which takes the characteristic, say, wavelength, which is the Planck constant h divided by the momentum p. Right? So h over p is the wavelength of this quantum particle, even though this is the particle that you know, for example, the electrons. Even though these electrons are particle-like object, but electron can actually go through this double slit and shows this interference pattern or diffraction pattern. And this is called particle is actually a wave-like material. And another very interesting side, another side of this particle-wave duality is that some wave-like existence or wave-like materials is really a quantum particle. For example, electromagnetic wave is really a quantum particle, namely a photon. Okay? So the light or electromagnetic wave, even though this is a wave-like object, but in quantum mechanics, its energy is really quantized. And the single quantized energy of electromagnetic wave is called a photon energy. Okay? So we usually use this h nu to represent such a quantized photon energy, which is the same as the quantized energy for electromagnetic wave. So electromagnetic wave in quantum mechanics is really a quantum particle, and which could actually scattering with electrons, and you get this Compton scattering, right? So Compton scattering is the proof that electromagnetic wave is really taking this particle-like behavior. If you collide the electron by a photon or by electromagnetic wave, then you could see this particle-like scattering probability that follows this, as if this photon as a quantum particle collides with an electron as another quantum particle. And the first aspect is, this particle is wave. You could actually see this, say, interference pattern or electron diffraction. So even though the electrons are particle-like objects, but when electrons pass through a single slit, and you can still see this wave-like diffraction pattern that only this light wave or water wave or whatever wave that could give you this phenomena. But the electron can also give such a phenomenon as electron diffraction, which is a proof that this particle in a quantum mechanical world can take a wave-like phenomena. And that is called the particle wave duality, meaning in quantum mechanical systems, every quantum particle shows its two faces. So it's like you have double characters. Okay, so in the morning you're a happy guy, but in the evening you are very sad. Okay, but whether you are sad or happy, you are the same person. But in the morning I can see your happy face, but in the evening I only see you crying. So this is the magic of quantum mechanics, namely every quantum particle shows two faces, two sides of coins, but you can only see one side of the coin at one time. So you cannot see the double faces at the same time and the same location, and that is forbidden by Heisenberg uncertainty relation. But every quantum particle or quantum matter take this particle and wave dual characters. They have double characters, they have double faces, and one side of the face is the particle characteristics and another side is the wave-like properties. So all quantum matter show up these two different faces. But what face that you see depends on what kind of experiments that you design. Okay? So there's no single experiment that revealed these two characters at the same time. You can only reveal one aspect of these double characters each time, or for each experiment. So that's why they only show up one characters in every experiment that you design. For example, here, these electrons show up this wave behavior only if you design these experiments, allow this electron to pass through the single slit. But electron is electron. Electron is a particle-like matter, and you know that from Millikan drop experiments. But when you design this experiment, the electrons are waves. Okay, but electrons are still electrons, and so you will see if you can take a snapshot of this screen, you'll see many dots that are hitting on the screen as time goes by, and these dots accumulate more and more, and later on, you will see this kind of accumulated intensity of this diffracted electron pattern, and which exactly shows the wave-like feature. So likewise, the photon is actually electromagnetic wave is actually a wave, but if you allow this electromagnetic wave to hit the electrons, and by design, it is a particle scattering experiments. And so electromagnetic waves will show up as a photon. And photon is a particle. And a particle next to collide another particle. And therefore, from Compton scattering, you don't know the wave nature. You don't see the wave nature of electromagnetic wave, but only see the particle nature of the electromagnetic wave. You got this? Okay, so depending on how you design experiments, you only see one of these two faces for any quantum matter. And that is the essence of the particle wave duality in quantum mechanics. But this is actually related to another very important concept called Heisenberg uncertainty principle, and also quantization of energy, because all quantum matters shows at least particle nature, okay, in this duality. So the energy of this quantum matter is always quantized. For example, this h nu represents the single photon energy, or energy of electromagnetic wave in quantum mechanics sense. And you can actually count this quantum particle by counting the energy of this h nu, and therefore only integer multiple of the h nu is allowed in this electromagnetic wave systems in the quantum world. Okay, So if you observe this energy to be 2 times h nu, and you know immediately that there are 2 photons because this is the prefix is 2, and this photon takes this single unit of h nu, the energy, and so on and so forth. So all quantum mechanical objects shows quantized energy. So this is the link between 1 and 2. Because of the particle nature of the quantum matter, their energies are always quantized. But the third important ingredient in quantum mechanics is the Heisenberg uncertainty principle, or Heisenberg uncertainty relations, which says that the uncertainty or error bar in determining the position of the quantum matter and uncertainty of a momentum of a quantum particle, as a fundamental limitation. And this fundamental bound is that when these 2 error bars are multiplied together, this product is always greater than or equal to h bar over 2, where h bar is defined as h over 2 pi. And h is the Planck constant. By the way, the Planck is actually the first one who really observed this, this h nu as a unit of photon energy. And as I mentioned, because of this fundamental limitations of quantum mechanics, and you cannot see the particle and wave nature simultaneously in the same experiments, because if you want to describe the quantum particle or quantum matter, you need to really characterize precisely in a precise way both the position of that quantum matter and also the momentum of the quantum matter. In order to really describe your quantum matter, you need to tell me where this particle is. Where is the this quantum particle, and what is the momentum of this quantum particle? And you need to tell me simultaneously, in a 100% accuracy, these 2 information. For a classical object, this is easy because you know the momentum of this piece of chalk and also the position of this piece of chalk. So you can determine this 100% certain, but in quantum matter, you cannot simultaneously acquire such information, because if you want to know precisely the location of this quantum particle by making this error bar 0, if delta x is 0, then you know this location of the quantum particle exactly, right? And likewise, if you make this delta p vanish, which means that the momentum of the quantum particle is determined exactly. But this Heisenberg uncertainty relation tells you that you cannot accomplish both accuracies at the same time, because if delta x is 0, then whatever delta p is does not matter. 0 times the finite value is 0, but the 0 is less than this fundamental limitation of quantum mechanics, which is h bar over 2, and therefore this product has to be greater than or equal to this finite value, which means that you cannot have delta x and delta p both vanished, which means that you are not allowed to note in 100% accuracy the location and momentum of the quantum matter. And this is the fundamental limitation of quantum mechanics, and this is the essence of particle wave duality. You only see one side of the 2 phases each time. You are not allowed to see both phases at the same time. Okay, so this is really important. So time is up. So this is for today, and I will see you next lecture.